So if you remember from the story, plan 1 was the peasant's plan, and plan 1 was exponential. And the equation was y equals 0.5 times 2 raised to the x. We had a doubling pattern going on with the peasant's plan. And then plan 2 was the king's plan, which was also exponential. It had a starting value of 0.3 repeating, and then times 3 raised to the x. So this was the plan that tripled from square to square. And then plan 3 was the advisor's plan, and that one was linear. Y equals 5x plus 15. So this plan was just adding 5 from square to square, an adding pattern instead of a multiplying pattern. So the graphs of exponential situations and the graphs of linear situations look really different. So if we look at the graphs here, A, B, and C, right away it's pretty clear to see that we would match up graph A with plan 3 because it is the only linear one that's up there. We can see as well that the graph A does start at about 15. And if we look at the rate of change here, if we were to inspect that a little more carefully, we could see that we do have that adding pattern. And since it's an adding pattern, we see the straight line. You can see B and C are both curved shapes, and that's the sort of shape we're going to get when we have an exponential pattern. So then it's a matter of figuring out just which of these two curved graphs goes with which of the two plans. And if we look, the scale on the graph is consistent. On both graphs, the y is going up by 10s and the x is going up by 1s. So one thing we can do with these graphs is compare their steepness. And if you just take a glance at the graphs, we can see that graph C is steeper. It's climbing much more quickly than graph B. Again, we can see, but by maybe about square 5, we're way up here in the 80s. And comparing that to graph B at square 5, we're only, in the teens. So because of that fact, we can kind of conclude that plan 2 has the larger growth factor, is going to match up with the steeper graph. So plan 2 would match up with graph C, and that would leave plan 1 to match up with graph B. That doubling pattern leads to a curve that's not as steep as the tripling sort of pattern. So to sum things up, let's just write down some information about linear and exponential situations. Let's look at linear first. First of all, a nice synonym for the word linear is the word arithmetic. And arithmetic really kind of means the same thing as linear. And the big thing about being linear is that we have a constant adding pattern. A constant adding pattern. And that constant adding pattern leads to having the idea of a slope. We can contrast that a bit with exponential situations. So an exponential situation, the synonym we can use there is the word geometric. So geometric really has a similar meaning as exponential, and that has to do with a constant multiplying pattern. A constant multiplying pattern. So rather than adding over and over by the same number, we're multiplying over and over by the same number. In exponential situations, we don't use the word slope. We'd use the words growth factor. And later on, we'll also talk about the idea of a decay factor. So let's put that either a growth or a decay factor. Growth or decay factor. The equations of linear and exponential scenarios do look different. So the linear equation that we've used so many times is that equation y equals mx plus b. And then the equation does change for an exponential situation because the again, pattern changes from being an adding pattern to a multiplying pattern. So our equation that we use for our exponential situations looks different. Y equals b times a raised to the power of x. And remember, we need that exponent to get at the repeated multiplication of that a. And that a right there is our growth factor, or decay factor, but for now they've been growth factors. And the b is the y-intercept. And then, of course, for y equals mx plus b, we've already spent a lot of time with that equation. That m would be the slope, and the b is the y-intercept. So then just one word about the graphs of these sorts of relationships. So a linear graph, I just draw a quick sketch of a linear graph, and I'll draw an increasing one. With a linear graph, we have this constant sort of rate of change. We have this rise and run that's consistent. If I move over the same amount, I always move up the same amount. We have these nice even steps when we're looking at a pattern that's linear. If we look at an exponential pattern, we see something different in the rate of change. So let's take a look at an exponential graph. We do a quick sketch there, and you can kind of model your graph like one showing up above. So sort of a curved pattern that gets steeper. It increases in steepness as you move from left to right. It's getting steeper. And if we were to draw some sort of stairs, and I'm trying to make the horizontal distance the same, but you can see what's changing is that vertical distance that I climb. The vertical distance here is getting bigger and bigger because the situation is exponential. So to sum up here a little bit, linear patterns, we can call them arithmetic. We have a constant adding pattern, which means we have a slope. We use y equals mx plus b. We see a straight line graph and a nice even rate of change in that sort of stair-step idea. An exponential pattern we can also call geometric. It's a multiplying pattern with a growth or decay factor. We use this equation, y equals b times a to the x. The graph is curved with increasing steepness if we're looking at a growth situation, and we can see those stair steps are no longer as even as they were for the linear situation. So hang on to this page and use it to help you as you work on some other items today.